Now, now we're going to, so what we've talked about so far is just what we call point estimates. So we're calculating an estimate of some value in a population. So the important thing to remember here is there's many important things to remember, but one important thing to remember is that when you do a point estimate from a sample and you estimate a confidence interval, the confidence interval is about the population, not the sample. You're not saying the sample has a confidence interval of 95% confidence interval of something. You're saying the population has a 95% confidence interval. Okay, you're talking about your degree of confidence about what the median is in the population, not in the sample. You know what the median is in the sample because you've got it. It's the nature of medians, but you don't know exactly what the median is in the population, but you can estimate it from a sample. And a good way to present the estimate is as a confidence interval. It's a pretty standard way of doing it. Sometimes I've written confidence intervals are often written between square brackets, as you'll see we've done there, for example. That's one fairly common way. You'll often see that in research papers in the social sciences, in psychology and so on, behavioral sciences. You'll see confidence intervals written like that. In other sciences, they're very often written as plus or minus. So you'll get, it'll be the median, and then it'll say plus or minus, and the number that comes after the plus or minus is 1.96 times the standard error. And then another thing you will see sometimes people talk about is the margin of error. So when a political pollster says that support for Joe Biden is 45% plus or minus, 45% with a margin of error of 3%, what they mean there, I need to just remember now. Actually, I might need to go back and check that. I'm pretty sure the 3% is 1.96 times the standard error. I think that's right. Okay, you can easily check that. All right, so now the next thing we might want to do is compare the medians of two samples from what we think might be two different populations, or we know are two different populations. Now this is what happens here is in the previous case with the point estimate, we actually have a formula which gives us a confidence interval. When it comes to comparing two medians, I'm not aware of a formula that does the job. There might be one, but if it exists, it's probably very complicated. So what I'm going to show you is some graphical methods that we can use, and these are perfectly sound. These are based on very solid statistical equations and so on. They're not just made up, and they're not hopelessly rough approximations or anything like that. They could be perfectly well used in scientific papers. They aren't a lot, but they could be. There's no reason why they shouldn't be, but certainly in a business context, this sort of thing is quite handy to know, because you can look at two box plots and you can make a judgment about your confidence that the medians are different. Some of you will have learnt this in high school or even middle school. I'm pretty sure it's part of the Australian curriculum. I know it's part of the New Zealand curriculum. But it's like many things. You learn them in high school, and then you don't need to use them again, and they just sort of evaporate. And there's nothing to be ashamed about if that happens. But I think for as you're moving through your degree and you're moving into the workforce, or you're in the workforce already, this is actually useful stuff to know. So the first one is a pretty straightforward case. So what I have here, this is real data. I got hold of quite a large data set actually about avocados in the United States. And this is data about the Hass avocado, which is the most popular one in Australia as well. This is the staple avocado for smashed avocado on toast. So what I have here is a sample of prices from across the United States of retail prices for one avocado, and there's two groups. So one group is organic avocados, organically grown avocados, and the other one is what they call conventional avocados, i.e. non-organically grown. And so we have the box plots there, and we have, with box plots, there are 2 or 3 rules of thumb you can use. By rule of thumb, I mean they are guidelines, but they're very well established guidelines for making some calls about your confidence in the difference of the medians. So this is kind of the simplest case. This is the case where the 2 boxes don't overlap at all. Okay, and you've got a reasonable sample size. So your sample size probably, for many kinds of tests, 30 is a sort of go-to number for sample sizes. You have to start being very careful when your sample sizes get lower than 30. So it's a rough guideline. 30's probably okay here. You know, if it was 15 and they looked like kind of ordinary box plots, they weren't kind of squashed into a single line or doing strange things, you could use this test and you'd be okay. So the simple fact that they don't overlap, that means you can say you are at least 95% confident that the medians are different. In truth, you could probably say you're 99% confident, but most people would just go with saying at least 95% confident or just highly confident. Okay, but if you see that pattern, 2 box plots, the boxes don't overlap, and there's nothing really weird about the box plots, and there's nothing weird about those. This test is not affected by, you know, a few outliers. You can express a high degree of confidence that the medians are different. So what are the...
Ed, I have a question. Sorry. So you said instead of saying 95% confident, we could just say highly confident. But would it be wrong if we said 95% confident in this?
No, it's not wrong. Okay. So you wouldn't say exactly 95%. You'd say at least.
All right. Thank you.
Yeah, because I think in most situations, if you saw a pattern like that, it would be more like 99% confident, but you don't know the exact number. So you can say at least 95% confident. The reason I suggest sometimes you know, particularly if you're giving a presentation to an audience about something, so you've done some sort of a study or survey, or you've collected some data, and you're working and you're giving a presentation of your results to people in the company or the organization, and you say, I'm 95% confident that the medians are different. There's a chance that there'll be somebody in the room who's done a couple of statistics courses, and they will want to know the details of how you did the t-test, or did you bootstrap the, they'll want to get into the detail, and that 95% number will be like a trigger to them. Some people just get kind of triggered into wanting to get into the statistical detail. It doesn't just annoy you as the presenter, it annoys other people in the audience as well. So sometimes it's just better to say you're highly confident, and then if somebody says how confident, then you can say at least 95% confident. So that's just a bit of sort of practical advice about the real world when you're presenting stuff. You don't want to, in many situations, you don't want to put any more kind of statistical jargon than you need to. But if you see that pattern like that, you can be very confident in making that claim about the medians being different. It is a claim about statistical significance, what you're actually saying, but again, I wouldn't use this terminology necessarily. It's not wrong, but what you're saying is that the medians and the two populations are, the difference between them is statistically significant. You're not getting a p-value, but you can certainly make a claim of statistical significance. And if you did some other test, you would come up with a p-value that was less than 0.05. Okay, so it's a perfectly good way of making this judgment, and it doesn't. The good thing is, it doesn't involve you having to. So for those of you that know about t-tests, of course you can do this with a t-test, except you've got outliers there. So let me just say a few words to people who have studied t-tests. There are some arguments against using a t-test. So one is you've got outliers. Okay, that's a problem, and you'd need to do some checks and things to make sure what was going on there. The second thing you've got to note from the box plots is that you've got unequal variances. Okay, this one's got a wider IQR than this one, and in that situation you have to use a variation of the t-test, something called the Welch-Satterthwaite adjusted t-test, to take care of the difference in variances. And then you also need to check if they're roughly normally distributed, which I would say they are. So people who are using a t-test, they've got a bit more work to do, and they might find that the data is not well suited to the t-test. This is probably okay, but it's the thing about this box plot test is it will handle data that you really wouldn't use a t-test for, and so then you would have to go on to some other test. Okay, so the point I'm trying to make is this is a good test. Okay, it's perfectly viable test, and you can use it in real world situations, and you can make a claim about, you can say at least 95% confident, or you can say highly confident, but and it's not, this test is not affected by having a few outliers in there, or different variances and skewed data. Okay, it's quite a robust test. Okay.
Ed, so if it says the sample, so if we say that we can only use this when the sample size is greater than 30, that's if the sample size is 31. Is that correct?
Look, so why I'm saying 30 is that gives quite a margin of safety with this. If you had two box plots that looked like that and your sample size was 15, it'd probably still be fine.
Okay, so let's say you asked
yes.
a similar question in the exam, and the sample size is I don't know, 15 or something. Yeah, we could still use this rule of thumb.
I'm probably not going to trick you like that.
Okay, all right, thank you.
But the point is though, Mickey, is don't, if your sample size is 28 or something, you'd be fine.
Okay.
Just a rough. But you'll find, if you study statistics, you'll find for lots of different types of tests, people will say to you, oh, look, 30 is a safe sample size. There is no, I'm not going to go into it. There's a historical reason for that, but let's not get too diverted on that. Okay, so what can we say? Okay, so let's think about samples and populations and things here. So the population depends a bit on what we're trying to do here. So if our question is, in 2020, what was the average, was there a difference in the average prices of organic and conventional avocados? Our population is then made up of every Hass avocado that was sold retail in the United States, and that's what we were able to get a sample of, and that's what we would refer to in the statement of our results. If we were using this to try and generalize about future sales of avocados, we would need to be mindful that we can't sample future sales of avocados. But there are many situations where where our population is something in the future. Okay, when we do market research, if we want to research market customer satisfaction, or maybe let's try something different. You do a survey where you ask people about their intention to buy the latest version of an iPhone. What the population you're really interested in is the population of future iPhone buyers or future buyers of that model. But you can't sample the future buyers necessarily because you don't know who they are. Okay, so you survey a bunch of people and you try and make a projection. So we often find ourselves in that situation, and what we have to do is the best effort we can to ensure that the sample that we can get today is as representative as possible of the sort of people who are, in that case, potential buyers of the newest version of an iPhone. So this is one of the things that I think can get the whole business of statistical inference rather confusing for people, because again, a lot of textbook examples are just things where there's a very clearly known population. You know who they are, but I mean, you don't necessarily know exactly who they are, but you can define them clearly and they already exist, and you have some mechanism for getting a sample from them. Whereas often, we, to give you an example, say you wanted to do some kind of survey currently to find out something about people's opinions or attitudes in Afghanistan. Afghanistan hasn't done a census for at least 20 years, more than 20 years, as far as I know. It's not a country where everybody is sitting on an electoral register and, with a street address and you can take a random sample. It would be very difficult to get a representative sample of a population like that. You don't even know how big the population is. You don't know where they all live. Okay, that's a really tough example. Australia's a bit different to that because, we keep pretty close track of who's living in Australia. It's still not easy. It's not straightforward, but you can generally do a reasonably good job of getting representative samples of the Australian population. But many countries, that's not easy at all. Okay, so we can say we're at least 95% confident that the median price of all organic avocados sold in the USA in 2018 was higher than the median price of the conventional ones. And again, we could say highly confident instead of 95% confident. So that's the simplest box plot comparison rule. We'll look at another one in a moment, which is a little bit fiddlier. You'll get to some point, and this will differ from some, between people, where some of these rules, they just get too complicated. You think, no, I'm just going to do a t-test or some other kind of test rather than, sit there with a magnifying glass looking at box plots. But that one's a no-brainer. I mean, this is very straightforward. Okay, it's 5 o'clock. Let's take a break for 5 minutes, and I'll stick around if people want to chat or ask questions, and then we'll get going again at 5:05.
Ed?
Yep.
When are you going to give us some information about the assignment that's due in November?
Tomorrow.
All right.
Yeah.
Can I ask a question?
Yep.
Where does that 95% number come from? Like, what's it based on? Why can we say that we're 95% confident?
Okay. Now, I've actually forgotten, Bianca, whether you've done a statistics course.
I have not.
You have not. Okay. It comes from ultimately from the area under a normal distribution. So, this is a bit like the probability density curves. I'm not very good at drawing normal distributions, but let's say that's a normal distribution. So let's say we'll just consider the organic avocados here, okay? So if you collected all the prices in the population, okay, and you charted them like this, and so on the y-axis you had frequency, okay, and the x-axis was price, okay. So you might have sort of some crazy prices up here where, I don't know, what's our highest value? I don't know. Was it about 2.5? Yeah, okay. Well, the highest one somewhere up here at about 2.4 or something. I don't know, 2.3 say, okay. And then your lowest one, yeah, it's about there 50 cents or something like that. Okay. So the idea of a distribution like this is that if you went to shop for an avocado, this tells you the probability of getting, actually this is not frequency, this is actually probability, sorry. This tells you the probability of getting of being hit with a certain price. So there's a very small probability of getting a 50-cent avocado and a very small probability of getting a $2.40 one. What you're most likely to get is about, for the organic ones, what is it, about $1.60 or something. Okay, say 1.6. Okay, so that's how any kind of distribution works. Many things have distributions that look something like that, something like a normal distribution. There are sort of good kind of theoretical reasons why lots of things end up being distributed in something like that shape. So what we do if we want to find a 95% confidence interval is we would get all of our avocado prices and produce a density plot like that. Okay, and then we would draw a line down here and here where we got like the inner 95%. Okay, so you'd have 2.5% would be very low in there, and 2.5% would be very high in there, and then in the middle you'd have 95%. Okay, and those two little vertical lines there where they intersect the prices, that's the confidence interval. Does that make sense?
Yes, that does. So is that why we need box plots that look like normalish? It's because we want them to have a normal distribution.
We want them to be not. You can get some fairly wild looking box plots, you know. You can sort of get, you can get box plots that look like that with a bunch of outliers and things like that. Okay, you can get some pretty weird looking ones. When they get really weird, then you'd start to think, maybe this isn't going to work too well. But most of the time they come out looking something like that. Okay, often there's a difference in variance and there'll be a few more outliers on one than or another, but they tend to, particularly for anything that's you'd expect to be roughly normally distributed. And prices, yeah, probably, student grades, weights of things, lengths of things, they tend to come out roughly normally distributed.
Oh, thank you very much.
Yeah. So there are in statistics there are many statistic tests that have quite strict requirements that the data is normally distributed, and they get messed up by outliers. Okay, and we say that if they've got a strict requirement that it's normally distributed, we say they're a parametric non-robust test. And if they're badly affected by outliers, we say they're not resistant. So the mean and the standard deviation are neither robust nor resistant. They're parametric statistics. But the thing is, there's a hell of a lot, things like linear regression, which we've talked about a bit. I mean, that has requirements about normality and outliers. And when you actually do linear regression in earnest, you actually do all these checks to make sure that you're ticking all these boxes about normal distributions and outliers and various other things. There's quite a list of tests you have to do regression properly. That's why I don't teach you how to do it. I'd love to, but I'd have to spend 4 or 5 lectures taking you through all the rigmarole that's associated with doing it. And it's a bit of a dangerous thing if you don't know how to do all of that stuff. It's more dangerous if you're drawing scientific conclusions than it is if you're just using regression to predict things. If you're just using regression to make some kind of prediction about you know, prices or, you know, purchasing intention or something like that, then you're in the world of machine learning. And in the world of machine learning, you often don't have to be quite as worried about this this detail about distributions and outliers and so on. You just want to check the thing works and keeps working. But when you're doing anything that looks like scientific evidence gathering and so on, then you need to pay attention to these things. So the reason I teach this box plot thing is it's a solid test, doesn't require any math, and it's robust and resistant to outliers. Okay, what's the downside? The downside is actually it is not as powerful as something like the t-test. So it will miss cases where there is a statistically significant difference, a smaller one. Okay, so if there's quite a small difference, a t-test might pick it up, whereas the box plot test won't. Okay, that's kind of the price you pay. But if you use a t-test and you've got a bunch of outliers and it's the distribution skewed, your t-test is going to give you false results as well. So, you know, if you know how to do a t-test, you can do both. So what would happen if I looked at the two box plots and they overlapped a bit, then I might look at some other tests. I'll show you one in a moment. But I might also, if I think the data is suitable, I would do a t-test. And there is another technique you can use called bootstrapping that I would use as well. Okay, well, let's move on. Now, so that's that rule of thumb. So that's one to remember. Now, this is, the next one is a bit of a fiddly one, but sometimes you will get box plots where you don't have to look very hard to see that this rule applies. Okay, the example I'm giving you is actually one where there's a negative result, but I just am using it because it's from the same data set. You know, it's just to explain what you do here. So this is a bit different. This is comparing daily average prices in the US for avocados of all kinds in 2017 and 2018. So apparently in the United States, there was a whole drama in the United States because avocado prices were supposedly going out of control, and people were not going to be able to afford their smashed avo on toast. And I think that was probably when smashed avo was at about the height of its popularity. So the question is, you know, is there a difference between 2016 and 2017? So the two boxes overlap there, so we can't use that first test, but there is another one you can use, and it works like this. So I'll just enlarge this a bit so we can see what's happening. Okay, so we have I've drawn some vertical lines there on the chart. So there's two dashed ones on the outer. They show the first quartile, the end of the box, at the lower end of the two box plots, and the other blue line there, the blue dashed line, shows the upper quartile of the higher box plot. So we call the distance between them, we call that the observed visual range. Okay, so it's from it's the total range, if you like, of the two IQRs. And then the inner lines have got little dotted orange lines there. They are the medians. Okay, so we have the distance between the medians. Now, if where's the rule? Did I write the rule in there? Goodness me, did I actually tell you what the rule was? Goodness me, oh dear, that's an oversight. Okay, so the rule is if the distance between the medians, that distance, is more than 33% of the observed visual range, okay, then you can be highly confident. Again, that would be 95% confident. Okay, So in this case, it's a bit less. I don't know exactly what it is, but did I do the calculation? No, I didn't. Anyway, so this one, I have to confess, I don't really use this one. If I'm getting to this point, I actually work with the data and do some kind of test, but you can do this. So sometimes it's really obvious. The distance between the medians is way more than 1/3 of the distance between the Q3 of the higher one and the Q1 of the lower one. And so you can make a claim about the difference of the medians. Now there's another test, and this next one kind of supersedes this one really, but it does involve being able to do something with box plots that not everyone can do. So we have this thing we call a notched box plot. So this was a further refinement of the box plot that came out a few years after the box plot itself. The canonical box plot was introduced. And what these notches do is they allow us to look for a statistically significant difference of the median. So if what you see there is a notch there and a notch there, and if the two notches don't overlap, then you can be at least 95% confident that the medians are different. Now, the way those notches are calculated, just so you know, but you don't have to remember this, is they are actually 91% confidence intervals for the median. And if you do a whole lot of math, you can figure out that if two 91% confidence intervals don't overlap, then you can be 95% confident that the medians are different. And indeed, if two 95% confidence intervals don't overlap, I think you can be 99% confident that the medians are different. Okay, now you can create notched box plots. I don't think you can do it in Excel. I'm not aware that you can, but you can do it using that tool that you used for the task write-up for test 2. And that was one of the reasons. This notch box plot thing is one of the main reasons I've emphasized canonical box plots, and I got you to go through the exercise of using that tool, because this is a really useful test. Okay, so if you can produce notched box plots, then the comparison is pretty straightforward. Okay, you can look at it and you can say, yep, 95% confident or not 95% confident. In this case, they actually overlap very slightly. Okay, so if you do it in the in that box plot, that online box plot tool, there's a little checkbox you've got to tick there which says add notches. Okay, it's completely straightforward to do. It just pops in the notches. What you'll find, and we may see, I'm not sure if we'll have time, but we might see an example later today, depending on what's going on with your data, occasionally what will happen is the notches will get kind of inverted in on each other, but you can still interpret them. As I say, if we get a chance, we'll look at that today. So notch box plots. What I look at, if I'm producing box plots and I've got an interest in significant differences between things, I will just by default produce notched ones. Okay, they're just really useful. Okay, let's move on to another example. So now coffee beans. Now this was an interesting one. So when I came up with this example, I found an amazing paper about the geometry of coffee beans, and there's some really serious mathematics in it. Coffee beans are the subject, their shape and size and so on is the subject of quite intense study, and that's because it's very important to the process of coffee roasting. Okay, So our scenario here is coffee roaster is comparing raw coffee beans supplied by 2 different vendors, obtains a representative sample from 2 vendors. The dimensions of 60 beans from each sample were measured and plotted. Okay, so what does this show us? This is showing us the depth of the coffee beans. So coffee beans are actually measured on at least 3 or 4 dimensions, but one of them is the depth, which is basically the smallest dimension. It's the thickness of the bean, and that's quite an important thing to know when you're roasting coffee, because you know, a lot of coffee roasting is about controlling the rate at which the beans heat up and cook, and that's a big factor in that, is how thick they are, and the relationship between time and heat and being properly roasted is not a straightforward linear relationship. It's quite complicated. So if you're a coffee roaster, the ideal thing if you're a coffee roaster is you would like all the beans to come in the same shape and size, if possible, and there are reasons why you would probably prefer the beans to be smaller rather than larger. Okay, so we're comparing 2 lots of coffee beans here. In this case, now I think have I misstated this? They don't quite overlap. Yes, good. Just checking I got that right. So the beans don't quite overlap. So that passes our box plot notch test. Okay, so that's good. But we need to think carefully about how we state the conclusion here, because we need to think about the population and the sample. I might mention here that, you know, I keep talking about thinking about the population and the sample. That's a pretty good clue that there's going to be questions in the next test that require you to think about populations and samples. So you need to work on that idea. Okay. So in this case, really, what the coffee roaster here is interested in is it's really about coffee beans that are going to be supplied in the future by the 2 different vendors. Okay. The samples, we say, were randomly selected, but they were not selected from coffee beans supplied in the future. They were selected from coffee beans that the 2 vendors had available at the time that the samples were taken. And we might assume that some steps were made sure that, you know, taken to make sure that the coffee vendors didn't supply samples that were not representative of, you know, what they had in stock and so on. But you can imagine there are still potential sources of error here, because there might be fluctuations from time to time in the sizes and dimensions and sources of beans and so on. There's lots of possible other variables that can affect things here. But we can still get a picture which makes an assumption that everything else remains the same. So, and I'll just point out that this is a very common practice. It's called acceptance testing. It's done in many, many different situations where companies and organizations buy supplies from vendors, and they need to periodically or regularly test that the supplied goods or commodities or whatever meet certain specifications. Okay, and the way you do it is you take samples, you take representative samples, typically of what's been supplied, and then you do some sort of calculation or chart or something to check that what's been supplied is within specification, and the specifications will be expressed in terms of confidence intervals. Okay, so what you want to make sure is that the confidence interval for the thing that's supplied, typically what you want is for it to fit inside the confidence interval that you've specified as the standard for acceptance. Very common practice. And, you know, sometimes this is done in a very formal way. Sometimes often these days it's automated. But there are other situations where you might want to do it and you just need to do it in a fairly informal way. You don't want to take a huge sample. You just take a fairly small sample and you just want to do some sort of simple test. So the box plot test is one you could do, but you do have to prepare box plots for that. I'll show you another test that you can do shortly that doesn't require that. So stating the conclusion here, the terminology I've used, we're 95% highly confident that the depth of beans supplied by vendor 1 is less than the depth of beans supplied by vendor 2. So the way that I've phrased that is kind of implying that this is a conclusion we're drawing about what will be supplied in the future, but it is based on a sample. It's not based on that population of things being supplied in the future. It's based on a population of things that we've got access to today.
Should we say we're at least 95%?
Yes.
Okay.
That would be better. Depends. So, you know, in English, this can be interpreted, that statement I've got there can be interpreted as, people will often say that when they mean they're at least 95% confident. Okay, they won't put in the at least. So it's in you know, in the normal way we use English, that can be kind of interpreted as at least 95%. People often say 95% confident when they actually know, if they look at the numbers and whatever that they've got, that they're 99% confident. And the reason for that is that 95% confidence is, it's just like p-values of less than 0.05. They're just so commonly used. You know, everyone uses them all the time, and you know, when people that are used to this stuff, when they hear 95% confident, or what they're thinking is, okay, that's over the line. That's, you know, we know what that means. They don't really care very much whether it's 95 or 97 or 99. Okay. All right. Now, look, you know, if you hunt around on the internet, you will find some other ways of comparing box plots and so on, but they really start to get so kind of fiddly that I think you know, you've got to say to yourself, maybe it's time for me to learn some statistics and do it a different way. But they are, what I've shown you are some pretty common scenarios, and certainly that notched box plot one is quite useful to know about. All right, now